Good morning, 2021ers. This will be my second attempt at doing a Project 4 overview video. First one went down in a flaming pile of poo on account of audio trouble, but I think I've got that resolved now. Apologies for the late delivery of this video. It's just been a busy part of the semester for me as well as for you. Hopefully you've gotten a start on this at this point. But if not, this should serve as a quick introduction. There are two problems on the project that relate to the most recent topics that we've discussed. There is an optimization problem that hits on general knowledge of how to make code run faster in the presence of CPU features like pipelining and superscalar stuff, as well as favoring cache access patterns that are good for the architecture. And the second problem has you visiting a binary file similar to what you did in Lab 12 and using a memory mapping of that file to navigate it quickly using pointer arithmetic. We'll treat each of those in turn. The general idea for the first problem is that you have a matrix, which is a 2D arrangement of numbers, tremendously useful throughout scientific computing. And the operation that you're attempting to optimize is to square the matrix. This involves matrix multiplication, multiplying by itself. And should you be unacquainted with that algorithm, which is tremendously useful, you'd want to do just a bit of review. In short, multiplying a matrix by another matrix involves multiplying a row in the first matrix by a column in the second matrix. In our case, the first and second are the same, so it'd be ABC times ADH, the first row by the first column, doing a dot product between those two of element A times A, B times D, plus C times H. This gets you the upper left element in the output. Similarly, then, the upper middle element is first row by the second column, and upper right element, first row, third column, is first row by third column. Now, what you'll notice immediately is this is not hard to do. In fact, it's not hard to code. Providing code to you is this baseline version of it over here, and it's a triply nested set of loops. Typical naive matrix multiplication implementation is an n-cubed algorithm that actually occupies a tremendous number of CPU cycles out there. And there are exotic alternatives that get lower than n-cubed, but generally most normal matrix multiplications will use this approach, and you're not expected to do anything wildly different than that. However, one thing you should notice immediately is that the hand way of doing this that's encoded in this algorithm down here multiplies a row by a column. And we'll need to then traverse down a column, B, E, I, or C, F, J. And based on our discussion of access patterns in the memory system, and which are favorable, row major matrices in C will have a bad cache performance whenever you would go down a column like this. So to that end, your optimization efforts to make this routine go faster are going to require you to figure out another scheme to access the elements of the matrix to avoid going down a column in that way. The idea is then you'll encode this faster version in, let's see, where is it? A mat square optim version. So this is the baseline version, and you code a different version of it in this mat squared optim file in a different C file, and this is compared then against the baseline version, and we'll look for speed up to say if your version goes a little bit faster, then you get a few points. If it goes a lot faster, then you get a lot of points. We'll try this on a variety of different matrices. And importantly, then, you'll need to make use of the tricks that we've discussed in terms of optimizing code. The first of those is to try to optimize the memory access pattern, but there are several other suggestions given down here. For instance, hit the CPU pipeline and deploy to superscalar features by perhaps removing certain things like function calls, localizing data so that there aren't too many dereferences, etc. And then possibly unrolling some loops to make it go fast. None of that later stuff, the micro-optimizations, will have much effect unless you address the reordering of the memory access. And there's some hints about that in the diagramming over here, that if you abandon the notion that you're going to completely compute the upper left element in one go, and instead say, to avoid inducing a stride, I'm going to compute parts of this first row first, by multiplying, for instance, A times A to get part of this first upper left element, and then move over into A times B to get part of the second element, and A times C to get part of the third element over here. And then go back over and say, now I'll multiply B times ABC to get the sorry, b times def to get parts of each of these elements over here, and then multiply c times hij to add on additionally to the top row. You'll see you've completed the top row without ever having to go down a column. And this type of memory reordering access changes the algorithm subtly to favor cache access patterns. Taking that forwards then and rearranging the given loops that are up here in the baseline version and an optimized version should get you a considerable amount of speed at the get-go. This is all evaluated then on certain machines because we're looking for speed up in the presence of certain architectural features. So the login machines are favored there. And the scoring for it, as would be run in this matrix benchmark, it's evaluated according to a slightly complex scheme, but you don't have to worry about too much of that. The more speed up you get, the more points you'll ultimately arrive at. So allow me to demonstrate here, and we'll see several features of that. Jump over here to code, and as we often do, I'll need to get the code itself. So I'm just going to copy the link here for this thing, and I have a terminal open, so I'll use doodle wget for this. That should give me a P4 zip, so unzip P4 code. And then if I change into that directory, you'll see there's a baseline version. If I just rearrange here. In here is the sort of baseline version, and this is set up so that there's some bounds checking. You can only square a matrix if it is square in shape, equal rows to columns, and that's checked for here before invoking the sort of main computational part of it. And then in addition to that, you're given a mat squared optim file that's essentially blank. That over here, the same bounds checking is given, and you would write your code in this mat square version 1, which is called down here. The mat squared version 1 then, if you get some speed up in it, then maybe you sort of save that and copy it over to version 2 and make some additional changes, and then copy and paste to a version 3, etc., changing which one you call down here each time. And this allows you to preserve several different versions of it so that you can test out whether or not certain things you add to the code lead to speed up. Right now, if I were to just bop over and do a make, let's see, I can't remember if I have a prob1 program. No, okay, so I'll just make mat square benchmark. Because I gotta have to be in the, the right directory for this. Square benchmark, and if I run this, there'll be several notable things. I'm not going to bother to run this to completion because you'll see several things here. First, I'm getting warnings because the evaluation is supposed to happen on the CSE Labs remote login machines. And so that's checked for by the benchmark and will warn in the event that you're not on that. This is running on my laptop, and so the timing evaluation is going to use the hardware on my laptop and may not be reflective of the architectural features you're optimizing for that are present in those login machines. Second, since my current optimized version isn't doing anything, it's producing incorrect results, which will lead to 0 points every time. One easy hack to sort of get me off the ground there is just to copy over this code for the baseline version into the version 1 that's called over here. Now, I don't expect any speed up here, but at least I'll produce functionally correct results and can sort of see the benchmark run to completion. So I bop down here and recompile and then rerun the benchmark. Now I'm still getting the warnings about the machine that I'm on, but at least I'm producing correct outputs of squaring the matrix leads to correct numbers there. If you try to speed up and produce incorrect results, you'll get 0 points because we're not interested in incorrect results. Fast, correct results there. That's harder to get. However, you can see I'm getting almost no points over here, and that's on account of me doing the exact same as the baseline version. Doesn't get any speed up. I'm not going any faster. That's because I'm doing the same thing, and that leads to no points. So the next steps then would be, I'm going to just I'll let that run to completion. You can see down here my CPU is just grinding right now, and I imagine the login machines are busy right now as folks are working on it. Next thing you do would be to start looking at this thing and trying to figure out, like, I see some function calls, maybe using some macros wouldn't be a bad idea there. There's some loops here. I might pick one to unroll, but most importantly, I have to figure out first, before any of those other optimizations would take effect, I have to figure out how to rearrange the ordering of this loops so that I don't ever go down a column. And you can see here this second loop has a J here in it. This innermost loop rather has a K in it. And while K is moving across a row, in this part it's moving down a column here. So I stay in the same column and go to different rows, which goes down a column here. And I'll need to figure out a way to get rid of that. Use those pictures that are in the project spec down here in the optimization suggestions to guide how you might rearrange the code for this to try to improve performance. All right, that's about as much as I'd want to say on that part of things. The next problem is ShowSim, and it serves two purposes: to acquaint you a bit with the executable and linkable file format, which is what all of the A.outs, executables, etc. that we have used, .o files, that's the format that this comes in. It's fairly extensively documented. We've talked about it in lecture now over the last few sessions. And it's a binary file format akin to what you'll have studied in a recent lab. I believe it was lab 12, where you had some department data with email addresses in and so forth. So this is an important format, but it's also representative of how to navigate binary files. And you'll use tactics to extract information from it, similar to what you did in lab. There are existing utilities for this already. For instance, we'll be targeting the symbol table, which lists in the elf file the global variables and functions that are present in it. And the readelf utility, which is installed by default on most Linux systems, it already has the capability to do this, and we're going to be recreating the magic of that as a learning exercise. So if you had a little .o file over here and ran readelf-s on it, the -s is short for show me the symbol table, then you would see over here some listing of the global stuff that's present in that symbol table. Now there's some gobbledygook that's bad over here, but typically the later entries in this will be things that are either global variables or functions that are present in the .o file that have been compiled down from C. For instance, the func here very much indicates this is probably a function, and this object designation here means it's data that can be referenced within it, not object-oriented by any stretch. So the program that you'll write, called ShowSim, and we'll take a look at the template for this in just a second, does similar things in that you compile this thing and then run it on a little .o file like this, and it'll print similar information to the stuff that the built-in readelf utility does, including then down here saying, oh, this max size, it's a function, this choices, it's an object, this list get, it's a function, etc. along those lines. As well as then doing some cursory error checking to say, like, oh, this thing is meant to work on object files, not on C files, or not on like other things that don't have symbol tables in it. So to that end, there is a need then to understand something about the ELF file format. Right? Before we do that, just look quickly, because I think my benchmark is done over here. I got all of 0.44 raw points, 0 out of 30 on the benchmark here. Just bear in mind for this first problem, you can get above 30 without too much trouble, but then it's truncated at 30. If you get a significantly higher score than the required, you may unlock some bonus credit, and a careful analysis of the code that's around in the project would reveal what is the threshold there, although it takes some creativity and optimization teeth in order to actually get that kind of result. You'll know it when you'll see it, because something interesting will happen. But aside from the mat squared stuff, then there is a single file, showsim.c, that's present to enable you to get started on the second problem. It is a template, more or less, where certain parts are marked as provided, and these largely don't need any changes. However, certain parts will be marked with question marks or some capitalized heading to say, you'll need to make code changes in here in order to get this thing off the ground. And so, for instance, you'll want to do some things to memory map a file akin to what you've done in lab recently and what we've seen in lecture. You'll need to then do later on some pointer arithmetic to say, hey, I need to point this header file or this header struct at some spot in the file that contains some binary information that I'm going to dissect for the next few sections. And once I do that, I can figure out where something else is in the file and point at it and so forth. So this isn't a write from scratch. If you fill in the parts that indicates that they need attention over here, then you should be good to go. Now the general flow of this thing is interesting. Similar again to what you've done in lab, that the ELF file format starts with a header, which more or less is a collection of bytes that corresponds to a struct in C. And the reference for ELF stuff that you may wish to read it describes each of those structs. For instance, you can find it in the manual pages, but clicking on this will take you to a web version of those manual pages. And so you'll see like, oh, the first thing that's in there is this e-header type, which is the thing, and it has all these different fields in it, which are described then in the subsequent documentation. Later on in the file, there'll be other struct types. For instance, someplace else, there'll be a program header, which we're not terribly interested in. Section headers, which you will be interested in. We'll allude to that later. And various other things, including a little lower down here, if I can find, the string and symbol tables. So there's descriptions of those things there. So this reference then can fill in the blanks for information that's absent from the spec or alluded to in the project specification over here. As a sort of gross survey of this, I have some pictures to assist. So the very first thing in the file is this goldenrod section, the ELF header. And similar to what was done in lab, this gives some identifying information to the file, but to say what type it is, as well as revealing where certain things of interest in the file may reside. The first phase of the program is looking for this, how is it, a pink section? I don't know how to say fuchsia, but pink is good enough for now. It's essentially a table of contents, the section headers section for the entire thing. It has an entry here as an array of structs for each of the other colored sections that are in here, of which there are a bunch that we're not interested in, but a few that we are. And so this goldenrod section indicates at byte offset 5000 from the beginning of the file. That's where this pink section starts. And you know from the documentation of this thing that each entry over here is a struct of a certain type, will have certain fields to it. And so this information that's present in the header allows you to find the table of contents and then traverse it. And you'll see in the code there's sort of smacks of a loop to say go over each of these entries and check to see what its name is. This table of contents then is interesting in that it has access to names for each of the sections, and they're mentioned over here on the left-hand side, but the actual data that's in the struct doesn't have any string names. So the .text or .sim tab as a string doesn't appear over here. It instead appears in this purple section, which is titled the section header string table. So string tables factor prominently in the ELF file format. They're an interesting engineering device. What you'll see then in each of these entries is a number that says my name is at offset 6 into this section header string table section. So if you went 6 bytes in from, if this starts at 1000 to 1006, then there'd be the name sim tab here as an actual ASCII string that's null terminated conveniently. As you would look at this entry and say, if I went to byte offset 14, that's 1014 here, sh stir tab, BSS, RO data. Each of these numbers here corresponds to a position in the sh stir tab of a name for what this section is. And that's cool. And it seems like all's well until you realize, wait, in order for me to know where the purple section is here, I have to figure out where the sh stir tab is in this part. And in order to know which is the sh stir tab, I need to know the names of things, which is in this. And it seems like a circular argument that needs some way to break it. The way to break it is to look up again in the header to say, there are 6 things in this array, and number 2 in it, this entry right here, this is the purple section. And so you can immediately find a pointer via this offset over here to this purple section. So as you traverse, you can look at names over here. That will take just a little bit of some wrangling on your part to wrap your head around, but once you get it, you're like, oh, I get it. It's like the names that I'm looking for are over here, so I'll just use some pointer arithmetic to get that over there. Then, once you have sort of traversed this thing and looked for certain other sections, what you're mainly interested in finding is the brown and green section out of here. They're labeled as Sim tab, that's number one over here, and Stir tab, no SH about it, which is entry 3 over here. And you can see the byte offsets 600 and 500. That's information that you'll record after traversing sort of this set of loops. And then you basically repeat that thing, that process. The symbol table is comprised of a bunch of different structs. Each of them is a global entity, a variable function or something else like that that's been baked in from the C file into the .o file. And so you'll see things then there that more or less correspond to like, oh, a choice is global variable or max size function or something like that. Again, the names for these aren't present in the structs. They're instead ST name fields that say within the brown stir tab section, how far do I need to go in order to find the name for this 11th thing in here, which is max size. So if this one starts at 500, if I go 14 bytes in, then you'll see, oh, there's actually the ASCII string max size there, so I can print it out in the symbol table. So traversing this thing and then printing out its entire contents along with some information about what type each thing is, how big is it in terms of bytes, etc. This is more or less the point of the program. There is a possibility that the symbol table doesn't exist, and this is sometimes called a stripped executable or stripped object. Usually you can only do it at the point that you actually have an executable. The symbol table itself isn't needed at runtime. It's used for linking purposes only. So once you produce a program, you can discard the symbol table, which is what the stripping sort of does. It helps to disguise information if you're trying to release to a customer, but really interferes with debugging a lot if you ever wanted to revisit that program. At any rate, that should give you a brief sort of dive into the second problem as well. This is due on Monday, although we will accept submissions up to 2 days late. So happy hacking on that, and I'll see you soon for our last class.